How's everybody doing? Good. Nice break.
Yeah. Are we planning this Friday to have another makeup class?
I can't do it this Friday.
Okay.
Yeah. I'm going to try to squeeze in as much as I can over the next few lectures. And actually, I think what I'm going to do is I've got a homework assignment. I've gotten mine. And I'll probably just make that the final exam. Okay. Yeah, it'll count just as much as the homework, but it'll be, I'll put midterm or final exam in quotation marks. Okay. And we'll just make that do. I'll type it up maybe tonight, and then put it in Dropbox, and I'll figure out when the due date will be. Okay, but it'll be on computing, amplitudes and matrix elements for QED. Okay, because I don't want to waste. I want to try to, like I said, I want to try to push as far as I can before class is over. All right. Anyways. Okay, so last time, I got to remind myself, we were looking at E plus E minus, goes to mu plus mu minus, but instead of computing the unpolarized cross section, where we basically just wipe out all information about spin by summing over it, here what we wanted to do was to compute explicitly the various spin states, both in the initial and final state. And so we were trying to do that, right? And we had started by writing down our amplitudes like we did for the unpolarized case. And what we wanted to do was still use this expression, but in order to specify either left or right-handed particles, we introduced our helicity projection operators, or just what I call projection operators, which we had seen before. And we introduced these guys, we put them wherever we want. So if we were interested in computing, an initial state that had a right-handed electron, we would put the right-handed projection operator right in front of the
the spin is enough.
Oh, sorry. I made it three papers in before you guys told me.
I was too busy remembering what we were doing last Wednesday.
Okay.
Audio lesson.
For this. So what I was saying is that to get a right-handed spinner, we just insert these projection operators in front of the spinner, or moving it through. We found that. So we took that expression and moved that projection operator through, and we found that what we had was a right-handed spinner in the final state, but a right-handed spinner V, which corresponds to the antiparticle, that corresponds to a left-handed electron. Okay? So the annihilation amplitude basically vanishes when both the electron and positron are right-handed. Okay, so you have to, and we saw at the end, that this basically comes from conservation of angular momentum, spin angular momentum. Right, and that's general. Okay, so unless the E plus and E minus, which are in the initial state, have opposite spins, and the muons in the final state, as long as those have opposite helicity, we'll get a non-zero amplitude. Right. So out of the possible 16 amplitudes we had to compute, just by using helicity arguments, we were able to eliminate 12 of them. Okay? And so we wanted to compute these 4 surviving ones. So it looks like we started by taking the electron line apart and squaring it, and doing our normal thing of rewriting the sum squared in terms of a trace. And when we got to this point, we moved the projection operator over because we wanted to eliminate one of those gamma 5s if we could. And sure enough, we found that we got PR squared, so that just gives us PR. Right? And at that point, we could use identities that we had already worked out to get to get the trace. Right? So there's one trace that involves 4 gamma matrices, and one trace that involves 4 gamma matrices and gamma 5. Right? And so we were able to get that. We used the same thing for the muon line, right? And then we could put it all together, right? And we squared this out. And what we saw is that a trait that's kind of common to a lot of matrix element squares. That you get these really complicated looking expressions, but if you look at them closely and you play around with the algebra a little bit, a lot of times you'll see a bunch of stuff cancels out. Okay, and for various reasons, we saw that all this stuff basically canceled out. We were left with 3 terms. Okay, and when we evaluated the the contraction of the Levi-Civita tensor, we canceled off even more terms, and we were left with just 1 term. Right? And we worked in the center mass frame where we had previously worked out these dot products, and so we found that this particular matrix element squared went like 1 plus cosine theta quantity squared. Okay, and we plugged it in the cross-section formula. We were able to compute that. And then that was 1, and what we wanted to do was compute the other 3, right? And so to compute the other 3, what you basically do is you go back to that amplitude that we had written down, and you play with the signs of the gamma 5, right? Because when you flip the sign of the gamma 5, you're basically going from, say, a right-handed projection operator to a left-handed projection operator, right? So depending on what you want as far as a right or left-handed electron or positron, you just basically play with those signs, and then you go back and you just trace through that calculation that we had just done and make sure you change the signs where it's necessary, and you end up finding. So, for example, what was the difference that we changed? Here we flipped the sign of, or we flipped the velocities of the final state muons, and so we found the minus sign in front of the cosine. And here we flip the sign of, the velocities of the electron, positron. We found another minus sign. And then when you flip both, you get back to the plus sign. And like we said, the other 12 velicity cross sections were 0. And so when you put it all together, you should, those 4 terms, when you sum them together, it should give you the unpolarized cross section. You can easily see that when you square out these 1 plus or minus cosine theta terms, that you're going to end up with only cosine squared. Okay. So sure enough, we get the unpolarized cross section back out. All right, and then when there were some notes about the conservation of angular momentum, but we already said that we used that information already to reason that these velocities had to be opposite. Okay. All right. So what I want to do today is, having studied E plus E minus goes to mu plus mu minus, out the wazoo, now we know everything there is to know about this particular process. I'm going to consider a different process. Okay. And this is going to kind of lead us into a nice feature in these Feynman diagrams, which is called crossing symmetry. Okay, so what I want to do is consider the process E minus mu minus goes to E minus mu minus. Okay, and so for this particular process, there's only 1 diagram. Okay, so instead of a diagram, well, let's see, I want to say the word yet. So instead of it going like this, it looks like this. Okay. All right. So we can use, use our Feynman rules to write down the amplitude. So here on this line here, I'm tracing along the electron line. All right. You can see the minus IE gamma mu coming from the vertex. And then I go along the muon line. I get the gamma nu. Here's the photon propagator. Okay. And when I contract everything, I get to here. Okay. So in order to compute the matrix element squared, I had to take the complex conjugate of that, so I did. And then when you multiply these two together, just keep in mind that the electron line pieces go together and the muon line pieces go together. Okay? And so when you do that, you can see that, for example, this piece is going to give you a P1 prime slash plus ME, right? And gamma nu, P1 slash plus ME, and then gamma nu, okay, coming from here. Okay? And remember, when you write these guys, when you take a complex conjugate, make sure you change the names of the indices, even though they're dummy indices, because they're dummy indices. And you don't want to start contracting stuff that's not contracted. It's not supposed to be contracted. All right. Okay. And so we can take our matrix element, multiply by m star, sum or average over the spins, and what we get is something that looks like this. Okay, so we have to evaluate these traces again. All right. But before you do that, it's helpful to go back and look at what we had for E plus E minus goes to mu plus mu minus. Okay, in the case the case we had before. Okay, and compare these two amplitudes. Okay, so this is our new process. E minus mu minus goes to E minus mu minus. Here's the process that we had studied before. Okay, and if you look at these closely, you can see a couple of things. All right, so first the prefactors, the coefficients are the same. Okay, but then you notice that, oh, wait a minute. If I take in this process, here we were calling the initial momenta P and P prime, right? But if I take P to be P1, right? P1 would have been the momentum of our electron, right? And what else? Take P1 prime to be minus P1 prime. So the minus P1 prime, so I'm taking P prime here to be minus P1 prime. Right? So that means I can factor out a minus sign. Right? And then down here I do the same thing where I'm replacing K prime with should be minus. It should be minus P2. Sorry. Minus sign here. Okay. And I can factor out another sign, right? And those two signs will cancel, and from this amplitude, I can get to this amplitude. Right? Is it clear what I'm saying? Mm-hmm. Okay, so you just make a couple changes in this guy, and you can get back to this. So what this means is we don't have to compute these traces all over again. All right? We can use the results that we had before, right? Right? We can use the results that we had for the traces before and just make these changes. All right. So that's what I do. So I take our, the result that we had for E plus E minus goes to mu plus mu minus, and I make these replacements. Right, and I can automatically write down the matrix element squared. Okay. So I don't have to go back and go through all that work again. All right. So what I can do now, what I have to do now is specify my reference frame, right? Because I want to evaluate these dot products. Okay, it's a little different this time because now we're scattering electrons off of muons, right? So it's not electron positron anymore. So there's going to be some difference in the kinematics, right? But you can still, square everything out or dot everything and find, what all these invariants are. And plug them in, okay, and I can get to this point here, okay. Yeah. Okay, so I've got my matrix element squared. I haven't done any magic, right? All I've done is use this, this observation that I can get E minus B minus matrix element squared from the E plus E minus by just making these changes. And then the next step is to apply your reference frame, right? And so once we do that, I can write it in terms of energy and momentum. Okay? And finally, I can plug this into a cross section. You have to take, here are the special cases. So before we had the case where the initial state particles are massless and the two final state particles are massive and have the same mass. But now what I want to do is have the case where one of the final state particles is massless and the other is massive. Okay, so we're neglecting the electron mass. All right, so I would, if I would, go back to the cross-section formula and compute that, I would see that the formula looks like this. Okay, so then I just plug in my matrix element squared, and I get here. Okay, where K, remember, is just given by the normal dispersion relation. And finally, you can take the high energy limit. So remember last time we were, we computed things, keeping the muon mass and treating the electron as massless, and then we said, well, in most of these experiments, the energy, the colliding energy, is a lot larger than the muon mass. So we can actually take the high energy limit and set the muon mass to 0. And in that case, we get something that looks like this. Okay? And one of the things that you note is that there is a singular behavior here coming from this denominator. Okay? You see that when cosine theta goes to 0, or when theta goes to 0, right, cosine theta goes to 1, and so you're going to get something that blows up here. Okay? So this cross section in that limit goes something like 1 over theta to the 4th. Okay? So as theta goes to 0, this thing's going to blow up. Okay? And if you remember from quantum mechanics, or even I think even in quantum mechanics, or maybe your modern physics class, really, you compute Rutherford scattering. So that's electron that coming in and it interacts with the Coulomb potential from a nucleus, right? Mm-hmm. And there you find the same behavior, right? You end up showing that it goes like sine to the 4th theta over 2 or something like that.
It is actually 1 minus cosine theta is equal to 2 sine squared theta.
Yeah, usually it's written in terms of the sine squared, but yeah. That's the way I remember it. But anyways, so it's the same behavior, okay? It's the same type of behavior that you observe in Rutherford scattering. Okay? All right, so it turns out that trick that we used where, we made a relation between the E plus E minus process and the E minus B minus process is an example of something that we call crossing symmetry. Okay? And the word crossing means exactly what you think it means in this case. So we started with, E plus E minus goes to mu plus B minus, and basically what we did was we took the E plus in the initial state, we moved it to the final state, and in the final state it becomes an E minus, right? And we took the mu plus and moved it to the initial state, and it becomes a mu minus, okay? So in general, so let me just state it in general. So the S matrix for any process involving a particle with momentum P in the initial state is equal to the S matrix for identical process, but with an antiparticle of momentum K, where it would be minus the original momentum in the final state. Okay, so in other words, my original S matrix or scattering matrix looks like this, where I have some phi particle that's incoming and has momentum P. This matrix element would be equal to the corresponding matrix element with this particle being replaced with an outgoing antiparticle that has momentum that's opposite of the initial particle. Okay, that's basically what we used in that using those relations by comparing the cross sections, or I mean the matrix element squares. Okay? And it turns out that if you really dive into it, look at the diagrams, that this relation basically just falls out of the Feynman rules, and the diagrams that contribute to these two amplitudes will have a one-to-one correspondence, right? So in other words, if I have, so in our case we only had one. So we only had one diagram, right? So here's our E plus E minus diagram, right? And so what I'm doing is basically, so this is, let's see how I want to do it. It's kind of crisscross, but what I'm doing is I'm taking E plus E minus goes to mu plus mu minus, and I'm turning it on its side. Okay, so it would be E minus. You had to flip. You need to move this guy over to the other side, but it doesn't change the structure of the diagram, right? Mu minus it goes to E minus mu minus. Making sense what I'm saying? Yes? Okay. So there's a one-to-one correspondence. So in other words, from that one diagram, we get the diagram that we had for E minus mu minus, right? But if there's more than one diagram that contributes to a particular process, then you're going to see that one diagram turned on its side corresponds to a diagram in the other process, and the other diagrams turned on their side correspond to the other diagrams in the corresponding process. Right? And these corresponding diagrams differ only by changing the incoming phi to an outgoing phi bar. Okay, so here I have a picture where I have some process, right, that's multi-leg, multi-initial and final state particles, and I have a phi and the initial state that's coming in with momentum p, right? But if I use crossing symmetry, that would be equal to this process where I still have this initial state, the original final state, but I've interchanged incoming phi with an outgoing phi bar, okay, the antiparticle, and this guy has momentum that's opposite the momentum going here. Okay. All right. So in the case, so here phi is general, so it could be anything really, scalar, fermion, or boson, or a vector. Sorry, vector boson. Okay. There are some subtleties which you might expect from crossing fermions. So in other words, when we cross an electron from the initial state to the final state, you're going to pick up signs. Right? There's going to be a minus sign. Okay. So the rule of thumb is for every crossed fermion, you multiply the total amplitude by -1. Okay. For that diagram. Okay, so in our case, we crossed an electron and we crossed a muon. So we've got two factors of -1. Okay, so that cancels off, and so we wouldn't have an overall sign. Okay. All right. Okay, so that's crossing symmetry. Okay, so you can see that once you compute one process that has whatever particles in it, and you're interested in computing other processes that have the same particles, you can always just use crossing symmetry, right, to compute the amplitude squares of those guys. Right, so that's the usefulness of crossing symmetry.
You just exchange two outgoing particles.
Yeah, you don't. I mean, you don't have to exchange. It doesn't always have to come in pairs, right? You can always. In our cases, it will because we're doing 2 to 2 scattering, right? But you can imagine some weird thing where you have 3 particles coming in and 2 going out, and you can cross one of them to the final state. Or we're gonna see later a process where we have a vector and a fermion, so photon electron scattering going into a photon and electron. Right? So we could cross, say, the electron and then cross the photon. Right? There we would pick up a minus sign because we're flipping one fermion. Okay. All right. So it's always good to use these things, these types of tricks, because you don't want to get bogged down in trying to compute these traces when you've already computed them. Okay, so next what we want to do is introduce something called the Mandelstam variables or Mandelstam invariants. And I know you guys here have already seen this, but let me just go through it real quick for the other people. Maybe you guys don't even remember the Mandelstam invariants, so I'll do it again.
I could probably use a refresher.
Okay. So what we want to do is express, or what we want to try to do is express the amplitudes or the amplitude squared in a more compact way, right? And it's for, several reasons. One is that, you just want to make the amplitudes as compact as you can because you got to plug these into a computer. And, the more compact expressions you have, the less computing time you have to worry about, right? But the other thing is it'll make more clear or, it'll make it a little bit easier to see these crossing symmetries and what you have to change in the amplitudes or amplitude squares, okay? All right, so we're always considering 2-to-2 processes, okay? So these invariants that I'm introducing are only good for a 2-to-2 process. Okay, so if you want to compute a 2-to-3 process, you have all new invariants. Okay. Okay. So we define. So here I have my initial state. It doesn't matter what kind of particles they are. So I have P and P prime incoming and K prime outgoing. Okay. And these Mandelstam variables or Mandelstam invariants are defined like this. Okay. So S is the sum of the incoming momenta squared, or the sum of the outgoing momenta squared. Right? So you see the two definitions for each one, but it's just using conservation momentum. Okay. T is typically taken to be the difference between the two closest guys. Right? So T would be this guy, and U would be how do I draw it? This guy with this guy. Okay, it's just convention. Okay, so if you look at these, you see that what you call T and what you call U is up to you, YOU, not up to whatever. Okay, so these are the Mandelstam invariants. They're invariants because they go like momentum squared, and they're nice because they, like I said, they'll make our expressions a lot more compact. So T and U are interchangeable, however you call them, it's up to you, but the expressions above, so the way I've written them down are the most common ways of writing them down. So T usually connects the particle and initial state, particle and final state that are most alike. That's just the unwritten law, unwritten rule, and QFT, right? But it's up to you. Okay. All right. So let's put these guys to use and see how useful they are. Okay. So let's look at our E plus E minus matrix element squared, and I'm going to work in the massless limit for the time being. Okay. So what we had there, so that muon mass term goes away, and we're just left with these products and dot products. Okay? And so the name of the game is to rewrite these dot products using these relations in terms of ST and U. Okay? So for example, P dot K, right? I can rewrite that as 1/2, right? And the quantity P minus K squared minus P squared minus K squared, right? You can convince yourself that if I multiply this out, sure enough, I'd get back P dot K, right? So if we're dealing with massless particles, these are the external momentum. So these guys are on shell, and they would be 0. Right? They're massless particles. So P squared and K squared are both 0. And this thing in here is T, right? So I get that this dot product is equal to 1/2 T. Okay? And you can go through all of them and do the same thing. So you get P prime dot K prime, again, is 1/2 T. P dot K prime is 1/2 U, and then the same thing for P prime dot K. Right? And then finally, Q squared, because it's the Q here is the E plus E minus. So Q here, remember, is the sum of the incoming momenta in this case. Right? And so that's just going to be, so Q squared will give you S. Okay? And so I take those guys and I plug them in to our expression here that is written in terms of dot products, and I get something that looks like this. Okay? And this is really nice, compact. You know that ST and U are invariant, so you can tell that your matrix element squared is Lorentz invariant, right? And what we'll see later on is that you can interchange. So when we write our cross section, it's always the differential cross section. We still have to integrate over the angular parts, right? The solid angle. And what we'll see later on is that you can actually exchange the the theta part of that integration with an integration over t. Integration over t. Okay. And so there, what you can do, it makes the integration a lot easier in the case that you want to compute the total cross section. Okay. All right. So, okay. So this is E plus E minus, right? So now let's see, using our crossing symmetry thing, what do we need to interchange between ST and U, okay? So if I look back at the interchanges I had to do, I had to change P prime to minus P prime, right? Because I'm moving that positron from the initial state to an electron in the final state. I had to change K prime to minus K prime, and then K to minus K. So I have K. I think this is K prime sheet. So, yeah. So K prime does not change. So keep it at a 5 state. Okay. So with these interchanges, I can go to my definitions of S, T, and U and look and see what they give me. So S is, we defined it to be P plus P prime, right? And if I make this replacement, P prime with minus P prime, I get P minus P prime squared, and that's nothing but T, right? And then if I look at my T for E plus E minus and replace K with minus K, I get K plus P. K plus P in this case is the sum of the initial states, so that's S, right? And then finally U, because P and K prime don't change sign, U just stays the same, okay? So in this case, the crossing symmetry means that to go from E plus E minus to this E minus mu minus process, all we have to do is interchange S with T, okay, in our expressions. And so that's exactly what I did to go from our E plus E minus expression to our E minus mu minus, okay? And you should check, go back to our original expression and plug in what S, T, and U would be for E minus and mu minus, and make sure that it should check out, okay? All right, so notice, I mean, these things look like, they're almost identical with just, the interchange of S and T, right? But just keep in mind that these guys have very different behaviors, right? So this guy doesn't have any, we saw that this guy had this angular, basically, divergence, right? As you take theta goes to 0, here you don't have anything like that, okay? So even though the matrix element squared look similar, just know that a lot of times the behavior can be very, very different.
If we go from U to T channel, do we need that minus sign still?
If you go to U to T channel, it would put minus sign. Oh, the minus sign is 5.
Interchange after.
No, because to go from T to U, all you're doing is crossing. I mean, you're just interchanging the two final state particles. So there you're not actually crossing to the initial state, so it wouldn't be a minus. You don't have to worry about a minus sign. Okay, and here's just some vocabulary. So in 2-2 scattering diagrams, where we only have one virtual particle, okay, so this would be like tree level type stuff, and not any loops or anything like that. We typically describe that particle as being in a certain channel. Okay, so for example, here my virtual particle is phi. Okay, and this looks like so phi here is, the denominator goes like S. right? So from this propagator. So we call this an S-channel diagram, okay? And likewise, here, the propagator goes like T, so we would say this is a T-channel diagram. And then finally, this diagram goes, the propagator from this guy goes like U, so we call this a U-channel, okay? The only time that you run into U-channel diagrams is when you have, well, I won't say that, but a lot of time, most of the time you run into them is when you have identical particles in the final state, so you have to consider T and U-channel diagrams together. Right, and this is just a note that a lot of times, you know, we've only looked at, so far, processes that involve only one diagram, but most of the time you're going to have multiple diagrams that contribute, okay? So one example might be E plus E minus goes to E plus E minus, which is known as Baba scattering, right? And so here you have that S-channel diagram that kind of looks like what we had, E plus E minus goes to U plus E minus. But because you have the same, the same particles in the final state that you do in the initial state, you also have this T-channel diagram. Okay, so the E minus goes right here, and here's the E plus. Okay. You also have molar scattering, which is the scattering of electrons off of each other. Right. So you have a T-channel diagram with the electron lines, but here in this case you've got identical particles in the final state. So you have to know that I need to consider a U-channel diagram in addition to this guy. Okay? And that just comes from the fact that you have identical particles. We can't, in quantum mechanics, we can't follow each particle, so we have to sum over possibilities. Okay? All right. So, I just want to really quick make a connection between the Mandelstam variables and our kinematic variables that we usually work with, like E and momentum or angle or whatever. And so I want to evaluate ST and U in the center mass frame. Okay? And I'm going to consider, for simplicity, a case where all the particles have the same mass, okay, mass M. All right? So what we have is initial state with P and P prime incoming, and K prime outgoing. Okay? And I'm just just using conservation of momentum, right? You can write down, and conservation of energy. You can write these guys down. So I can compute S, T, and U, right? So S is going to be the sum of P and P prime. Right, and when you sum these two guys, the three momentum pieces cancel off, so it's just 2e squared, and 2e is just the center mass energy. Right, so if you're in the center mass, each particle is coming in with the same energy. Right, so the center mass energy is the sum. Okay. Likewise, you can compute T and U, and you find that they have these forms. Right, so you can see a little bit. You can see what I was talking about earlier when I said that a lot of times you can exchange the integration over theta with an integration over t. Okay, just using this relation. Okay, and this p squared is the 4 momentum squared. Yeah. Okay. What else do I want to say? U is the same thing. You just get a plus sign. And just simply, just something that we noted earlier, that when theta goes to 0, t goes to 0. When theta goes to pi, u goes to 0. Okay. So this would be, how you would interpret ST and U in the center mass frame, okay, in terms of the center mass energy and the scattering angle. There's a nice, nice little relationship when you sum ST and U, right? And you can see it from these expressions that we have here. So when I sum ST and U, here I get 4e squared, and I get t and u. The cosine theta pieces from t and u cancel out. These two combine to give me 4, or minus 4 p squared. So I can factor that 4 out, and e squared minus p squared is nothing but m squared. Right? And so you can see that s plus t plus u is equal to 4m squared. Now, where does this 4 come from? It's the number of external particles, right? Because you can show, in general, for a 2 to 2 process, if you sum ST and U, you get the sum of the external masses squared. Okay? And this is a lot of times very useful in calculations because, say, you want to write your cross section just in terms of S and T, but you've got these U's popping up, right? You can so what you can do is you can actually use this relationship to replace U in all your expressions with, the sum of the masses minus S minus T, right? And then you can get your cross section in terms of S and T, and then maybe just do the integration over T, right? Because S is a constant. Okay. So that's the usefulness. So this, in practice, you use this guy a lot. Okay. All right. So just to summarize, the typical, this is going to be the homework. Oh, so you weren't here, so I'm going to assign one more homework, and it's going to be the final exam as well. Okay. But it's going to involve computing cross sections, basically. All right. So the kind of recipe is you take your process, you write the final diagrams down, write down the amplitude, compute the amplitude star, compute the matrix element squared. Doing that stuff, moving the spinors around, you take the trace. You'll get something that's written in terms of dot products between 4 momenta. Right? You can replace those with ST and U, and then if you want to simplify things even further, you can, if you have ST and U all in the expression, you can replace U with S and T in the masses. Okay, so it's that simple. All right, so the homework should take you like 15 minutes. Okay. I'm just kidding.
So the final exam is the homework.
Yeah. So we'll have class Wednesday and then Monday and Wednesday next week. Okay, and then the homework / final exam will be due, I don't know, a couple of days after our last class. Just long enough for me to
Before final grades are due.
Yeah, as long as I can check and make sure that All right. Okay. So we're okay. All right. So that's the usefulness of ST and U. Okay. And what I want to end with is the beginnings of a new process. Okay. So far we've only considered processes that have fermions in the initial and final state. Okay. But we've got another particle in QED, and it's called the photon. Okay. So there are processes where you can scatter photons off of an electron, or you can scatter electron positron to get photons out. There's a whole new world, okay, when you introduce the photon. All right. So what I want to do is consider Compton scattering. Okay. Compton scattering is when you scatter a photon off of an electron, and you get an electron and a photon in the final state. Okay. What was I going to say? Okay. Yeah. So this is going to introduce a whole new complication because remember from our Feynman rules that when you have external photons, you represent those by polarization tensor. Right? Remember, these guys have U's and U bars. These guys get their polarization tensor, polarization vector. Okay? You'll see what I mean. All right? Just a note here that every time you have two different diagrams or two separate diagrams, you want to check and make sure that you get the relative sign right. And here you would find that if you check it, you see that they do sum. There's no sign difference between these two diagrams. There's a nice if you look in Srednicki, he gives a nice kind of algorithm for checking the relative signs. Okay? Which I think covered, but it's in the book, so they might come in handy for the homework. All right. Okay, so I can write down the total amplitude for this guy, and this guy. Okay. So here's the S channel diagram, right? And you can see that as I trace along the fermion line, I hit this photon, right, which gives me the vertex factor. But it's an external photon, so I have to include the polarization vector, right? and it's being dotted into this vertex, right? It's a final state particle, so it's epsilon star. Okay? And then I trace along this virtual electron line, gives me the electron propagator. Okay, so I think this is the first time that we've had.
Move it to the right a little bit.
That way.
A little bit back. Yeah, thank you.
Okay. So I think this might be one of the first times we've seen virtual fermions. So we see the P slash is the numerator coming up. Okay. And then we can do the same. Oh, so then I would come through, hit this vertex, right, I call gamma nu, and I get an epsilon no star to nu. Epsilon no star nu, right? No star being it's an initial state particle. Okay. And then I go through and write down the same thing for the T channel diagram. Well, not the same thing, but you know what I mean. Follow the line. Okay. And what happens is you see that the gamma mu's and gamma nu's get flip-flopped, and obviously the propagator is different. Okay. But the nice thing is you can factor a lot of stuff out. So I can factor out, obviously, factors of I and the coupling, right? But I can pull out these factors of polarization vector. So I can pull it out front. Here's my U bar of P prime. So this is the final state electron. Right? Here's my U. Oh, I got two factors. I couldn't decide that already. That guy's gone. So here's my U bar P prime. Right? Here's my U. And then this is the stuff from the S channel diagram, and here's the stuff from the T channel diagram. Okay? All right? So you can take this guy, and if you were brave, or you just wanted to punish yourself, you could go and try to square this thing and compute whatever you needed to compute. Okay? But a lot of times it behooves you. That's the right word, right? To try to simplify things as much as you can. Okay? So for example, these propagators, the denominators, we can simplify those because if I actually square it out, this P plus, say, the P plus K, right, if I square that out, I get P squared plus K squared. Both of those are 0. Oh, no, I'm sorry. K squared is 0. That's the photon, right? But P squared is M squared, and that cancels this minus M squared. Right? So the denominator you can just write as 2 P dot K. And if you want, you can take it a step further and write them in terms of a Mandelstock variant. Okay, so this would be something proportional to S. Okay. And the same thing for the T channel propagator. Again, everything cancels except the dot product, and you could write that in terms of T if you wanted to. Another nice little trick to simplify things is to use the Dirac equation in momentum space. So remember, the Dirac equation in momentum space looks like P slash plus M UP equals 0. So if you remember back when we were first working through and deriving, working out these spinners, we wrote down a relationship like this. Right? So this tells me that if I move the M term over to the other side, that P slash U, P slash operating on U of P gives me minus M U of P. Okay? I think I did that algebra right. So what you want to do is, so when you see things like, here's my first name. Okay. When you look at this, okay, so K and K prime, those are the photon momenta, right? So those aren't going to go anywhere. But I look here and I see a P slash here, and I see a P slash here, right? So it might, simplify our lives a little bit if I can move that P slash. I'll have to move it through one gamma matrix. But once I do that, I can use this relationship. Okay? And a lot of times you'll be dealing in the massless case. So what this will Y you will be a 0. Right? You'll be able to cancel some stuff off. Okay? So that's what I'm going to try to do. I'm going to try to move the P slashes through. Right? And in fact, I'm going to take just the P slash plus M piece and move it through the gamma matrix. All right, so when I do that, obviously the mass moves right through, it's fine. But here we have to use the anti-commutation relation. Okay? So when I move p slash through gamma mu, I end up with, this was the 2g mu nu term, right? So it gives me 2 p mu, right? And then minus gamma mu p slash. Okay? Everybody know what I'm talking about? I'm using no paper there instead. I'm using gamma mu, oops, this is nu, equals 2 g mu. Okay? Can you see what I'm doing?
Yeah.
All right. So what I'm doing is gamma nu is 2g mu nu minus 8 mu gamma nu. Okay, so I'm just moving it through, right? And the fact that I have a p slash here means that the resulting, from the 2g mu nu term gives me a 2p mu. Okay. All right, and so then what I see at that point is that, and I just noticed I had the sign wrong, so this should have been minus. All right, and this is plus, that's right. All right, so what we have here is the p slash minus m hitting the spinner, and we know that that's 0, right? Because p slash on this guy gives me m, and m minus m, I'm pretty sure is 0. Right? So what it means is that this term just reduces to this. Okay. So what I can do now is rewrite it in a slightly simpler form. I can almost get it all in one line now. All right. But you can see that. So here's the k slash term that we didn't do anything to, and here's what's left of doing that little trick of moving p slash through for this term and then for this term. Okay. So this is where I'm going to stop, because the next step is to obviously take the complex conjugate and then square these guys, okay? Or multiply m times m star, and then we'll want to do the same thing that we did for the two fermion cases, is average over the initial spins and sum over the final state spins. Okay. So what we'll have to work out next time is how do we sum over these polarization vectors for the photons. Okay. All right. Okay. So my goal is that will finish off QED, and then I was thinking that I would skip ahead to non-abelian theories, in particular QCD. All right. So you can see a little bit of that before the semester's over. Okay, because it's important to see non-abelian gauge theories, because that's what the standard model is made out of. All right.
Do we quantize these epsilons?
Well, I mean, remember where they came from. They came from when we polarized, or when we quantized the photon field. Right. We needed something that carried the Lorentz index.
They're already quantized?
Yeah. I mean, they're just 4 vectors. Remember, because we wrote down, I mean, we basically just guessed at the form, but we wrote down the photon field in terms of annihilation and creation operators like we always do. But the photon field is a vector, right? So we needed something to carry the Lorentz index, right? And so we just identified that piece that carries the index as a polarization vector. Okay. All right. Okay. All right. So I'll just see you Wednesday. I'll let you know when I put the thing in the Dropbox. It'll probably hopefully be tonight. All right. Any questions? No. All right. See you guys Wednesday.
Thank you. Goodbye.
Bye. See you guys.
Okay.